Math 1314, Tyler Junior College, Section 2.6, Combinations of Functions, Composite Functions. In this series of videos, we're going to basically learn the algebra of functions, or another way of putting it, how can we take two previously existing functions and combine them to make a new function. In this video, or rather this series of videos, we're going to look at 5 ways to combine new functions. But before we get into the discussion of combining functions, we need to discuss a little bit more in depth the domain of a function. In the previous series of videos, when I was introducing some common graphs and their functions, I made a few comments about domain issues. For example, the function f of x equals 1 over x, we said its domain was all real numbers except 0 because it made the fraction undefined to have 0 in the denominator. Or for the function f of x equals the square root of x, we limited its domain to the interval 0 to infinity, including 0, because we wanted to avoid any outputs that were not real. By square rooting a negative number, it would have given us a complex number that wasn't real. We can extend the concept in both of those simple functions to give a more rigorous definition of the domain of a function. Now I know when we first looked at relations and domains and ranges, we said simple things like domain was the set of first coordinates, or domain was the x's, or domain was the inputs. And that's not entirely wrong. But when you have a relation that's represented by an equation or a function, the domain is implied. So we need to be a little bit more specific about what we mean by the domain of a function. We're going to find the domain of f of x as the set of all real numbers, x, that make the function both defined and real. Now, what do I mean by that? Well, we've already seen some instances of it, but let's be a little bit more rigorous. By defined, that means we want to avoid anything that makes the function undefined. And at this stage in the game, there's only one scenario that we classify as undefined, and that's having a 0 in a denominator. So for defined, what we mean is that we want to avoid denominator equal to 0. So how do we do that? Well, if we want to avoid something, we have to first find the thing we want to avoid. So, if f of x has a denominator, and more specifically a denominator that contains a variable, as opposed to say just 10, but if f of x has a denominator, the domain is all real numbers except solutions to denominator equals 0. In the back of my mind, I'm thinking to myself, but what if the function has other domain issues? But for now, let's just assume that we're focusing on a function with the denominator, like the top one over there. To find the domain, we have to solve the denominator equal to 0 and then state that the domain is everything except that. So let's go ahead and take a look at this example. F of x equals 4 over x squared minus 7x plus 10. With the question, what is the domain? Well, in order to answer that, we have to find the numbers that we want to avoid. And we want to avoid x squared minus 7x plus 10 is equal to 0. So let's figure out what those solutions are. Choose the technique of your choice. I'm going to factor this. You're welcome to use the quadratic formula. X squared minus 7x plus 10 will factor into x minus 5 and x minus 2. If your factoring skills are still weak, I recommend watching the video series called Factoring Review. But using the zero product principle, since the left side is factored and the right side is 0, we can simply set each factor equal to 0. X minus 5 is equal to 0 and x minus 2 equals to 0. And if we solve, we get x equals 5 and x equals 2. But be careful, that's not the domain. That is precisely what we do not want in the domain. We need to avoid these two numbers and get all the other numbers. So how do we represent a domain that's everything except 2 and 5? Well, think of it from a number line perspective. If we broke out a number line and located the two numbers we're avoiding, 2 and 5, put an empty circle in each one to indicate we don't want them, and then shade in the rest, we would need to write 1, 2, 3 intervals and join them together with a union. The leftmost interval, going all the way back to negative infinity, is negative infinity, comma 2. The middle interval between 2 and 5 is parentheses 2, comma 5. And the final interval to the right of 5 is 5, comma infinity. So we would just union them together. And so the domain would be negative infinity to 2, both with parentheses, union, 2 to 5, both with parentheses, union, 5 to infinity, both with parentheses. So if your function has a denominator, put it equal to 0 and solve it. If those solutions are real, get out a number line, remove those solutions, and your domain is whatever's left. If you solve the denominator equal to 0 and the solutions are not real, meaning that they have i's, then no real number would make the denominator equal to 0, in which case your domain would be all real numbers. Let's talk about the real part of the definition of the domain of a function. The domain is the set of all real numbers that make the function both defined and real. So in order to keep the outputs real, we need to avoid things that create i's, the imaginary unit. Well, that shows up when you square root a negative. So for real, we have to avoid square root of a negative. And for full disclosure, we need to also avoid fourth root of a negative, sixth root of a negative, and any even root of a negative, because cube root, fifth root, and all the odd roots of negatives are okay. So when we see a function with a square root, such as g of x equals the square root of 12 minus 4x, we need to avoid this. So how do we avoid that? Easy. If f of x has a square root, I'm going to put an asterisk after square root. I'll define it down here. The domain is the solution to radicand, which is the official name of the contents of a square root, greater than or equal to 0. Why greater than or equal to 0? Because if the part under the square root is greater than or equal to 0, then its square root will also be real. By contrast, if the radicand is less than 0, that means it's negative, and the square root of that would be imaginary. So we can force a function with a square root to avoid complex numbers, or rather avoid imaginary numbers, by requiring that the radicand is greater than or equal to 0. The asterisk is for any even root. So again, 4th root, 6th root, 102nd root. As long as it's an even root, we would do this. If it's an odd root, we don't have to worry about it. The domain is all the numbers unless there are other issues like denominators. So how would we find the domain of g of x equals the square root of 12 minus 4x? Well, we want to prevent the radicand from becoming negative by forcing it to be non-negative. So we solve 12x minus 4 is greater than or equal to 0, doing the moves that we do. Subtract 12 from both sides, you get negative 4x is greater than or equal to negative 12. Divide both sides by negative 4, which will make this a 3, but when you divide an inequality by a negative, you have to reverse the sign. So the action of dividing both sides by negative 4 would reverse the inequality, make it less than or equal to 3. We could break out a real quick number line if necessary. By the way, I forgot to mention that these domains will all be expressed as intervals. Here's 3. If we shade to the left because we're less than or equal to 3, then the interval begins at negative infinity, ends at 3, includes the 3, and there's our domain. In retrospect, this makes sense. If you pick a number less than 3, then 4 times that number will be less than 12, and so the difference will be positive. But if you pick a number greater than 3, 4 times 3 is greater than 12, this difference will be negative. Now this leaves one more small domain issue which only takes about 60 seconds to explain. What if you have a function that has neither a denominator nor a square root, such as this one? H of x equals x squared plus 11x plus 30. If your temptation is to set it equal to 0, stop. We want all real numbers except these. Are there any denominators to avoid being equal to 0? No. Are there any square roots to avoid a negative radicand? No. This function has no issues. It has nothing that could cause it to be undefined. It has nothing that could cause it to be imaginary. Therefore, there are no bad x's. If you have a polynomial function, the domain is all real numbers. Negative infinity to infinity. There are no numbers that we couldn't put in here. There are no denominators to make 0. There are no radicands to make negative. So no issues, no exclusions. Your domain is all real numbers.